sometimes I wonder if I will ever bother learning the Chinese script. As you probably know, I'm PR. I find the Chinese writing system, to be blunt, insults my intelligence. It's such an archaic, stupid system where you have to learn literally thousands of characters, each little squiggly wiggle for each character, to be able to read it and write it, compared with in fact I think every other country in the world which uses an alphabet. I mean, Japanese and so on, they use a lot of Chinese characters, but they have two alphabets, or syllabaries, which are almost the same. But China, as far as I know, is the only country in the world that does not use an alphabet in its writing. So it's an incredibly clumsy, stupid writing system. Most other Asian countries that did copy the Chinese writing system way back have since switched. The Koreans switched to a highly intelligent phonetic alphabet a few centuries back. One of the kings organized that. The Vietnamese, much more recently, Ho Chi Minh, the president at the time, same time as Mao Zedong. In fact, so he switched to a phonetic alphabet system because it's just so much easier to learn to read. A kindergarten kid can learn 24 letters in less than a week, whereas it takes almost to high school in Chinese schools to learn how to write their incredibly clumsy, conceptually stupid writing system. Anyway, that's the text, and it's a classic for good reason. And the fact that the Chinese, because I live in China, right? The fact that the Chinese have chosen to put this text in the Chinese format, more or less, for Chinese students shows that they consider that this is one of the best, and it's a classic. So, but it is 400 pages, so it'll take me a while. The present text is about 150, so I'm hoping it won't take more than twice as long. All right. Okay. After that diversion, so you got something similar to this in classical mechanics, like the electronic charge ER. You can look on that as a kind of dipole moment. Two poles, like two poles. More positive charge, negative charge, so you've got a kind of polarity to two poles, you've got North Pole, South Pole. So you have something sort of equivalent to this in classical mechanics, so you end up, this is a rate, right? So you talk about, in classical mechanics, a rate of electric dipole transitions. Now, it's just thrown at you for classical interest. Right, now there are problems with this rate formula, and the problems boil down to this term here. This what can we call it? Perturbation matrix. I think they've relabeled it and now calling it the dipole matrix element, analogous to the classical equivalent. Right? So anyway, they're just talking about this here. Now it could be that this term here ends up being zero, right? And that can happen. Like for certain choices of your initial state and your final state, it could be that this matrix element ends up being zero, and hence you conclude that the rate W is zero. And that's not the case because the assumptions we made here were that the dominating terms in the transition rate were non-zero, but when this term does go to zero, then you need to go to finer levels of transition. So the approximations you make then break down because of this if this happens. So what to do? Well, several things. In your modelling, you could then bring in, say, magnetic effects. So we've been talking so far electric effects, and we assumed that the speed of the moving system, let's say your atom with one electron or whatever, was small, so there are no magnetic effects. Now you may, if you've done electromagnetic theory, there's a famous formula, I can't remember what it's called, in the right hand screw rule. So the force on a moving charge of velocity v in a magnetic field B is the cross product of V cross B. So when this is zero and you predict the rate W is zero, that's not the case. There are still transitions. There's still a transition rate. It's just a lot lower, but it's still there. So you need to make a finer model. You need to consider sort of less energetic type phenomena, and one's bring in magnetic type phenomena considerations. So you assume that the speed of the system is not negligible. So there is magnetic effects. So then you get a magnetic term in your perturbation, that kind of thing. Another possibility is I'm trying to remember the term. Perturbation theory. You can go to higher terms, right? Not just lambda 1, but you go to lambda 2, lambda squared. So you can bring in higher terms. So there's several things you can do to overcome this problem, which does arise sometimes. Okay. Now, a general comment from the authors is if this sort of thing does happen, and you do go to, say, higher order effects in perturbation theory, lambda squared, for example, then these transition rates, the phenomena that cause these, the transition rate, that cause the transitions, they tend to be of much lower energies, and hence generate transitions at a much lower rate, so that your W is much less. Okay, so that's it leads into the next session. So stop there.